Unit 5, Thermochemistry, pages 32 to 40, heat capacity. Most materials experience an increase in temperature when heat is added. So here's aluminum at 300 Kelvin, and if you were to add heat, or if Q is positive, then it would increase in temperature. This equation governs how much heat is required to cause a certain temperature change. The amount of heat is equal to the heat capacity of your object times the change in temperature that would occur. Over here on the left is a chart or table of specific heat capacities. Notice the units are joules per gram times Kelvin. And these are specific heats for these different materials. These are constants, so they don't change. And they'll be given to you on the tests or any assessments. That's going to be in a unit of joules. Heat capacity is going to be total heat capacity, which is joules per Kelvin. When you're doing a specific heat capacity, then we're going to also have a mass unit in here. Change in temperature is in Kelvin, and change in temperature is always going to be equal to the final temperature minus the initial temperature. Every material experiences a different change in temperature when heat is added. Heat capacity, C, is the physical quantity that uniquely specifies the ability of a material to store energy. The total heat capacity, C, depends on the atomic structure of the material and the amount of material. A material with a large heat capacity stores energy efficiently. For example, water has a high heat capacity. When the sun heats the earth in regions along the seacoast, the temperature change is more moderate because the ability of water to absorb the sun energy. There are three ways that heat capacity can be specified. CS, which is specific heat capacity, and that's going to be heat per gram. This is what we'll generally be dealing with. But there is CM, which is molar heat capacity when it's heat per mole. And then there's C by itself, which is the total heat capacity, and that's joules per Kelvin. Over here on the left-hand side is the different ways that molecules can store energy, and it's through translation, rotation, and vibration. And so here is your rotation, here's your vibration, and translation would be moving side to side as opposed to rotating and then just vibrating. So based on the three different specific heats, we have three different equations. However, this is going to be the one you're going to use most often, that the heat is equal to the specific heat of your substance times the mass of your substance times the change in temperature. You're often going to see this equation written for me as Q equals MC delta T in short, which is mass times the specific heat times the change in temperature. Easy to remember when you write it like this because it's Q equals MCAT. All right, here is heat is equal to specific molar heat capacity times the moles times the change in temperature, and then this is total heat capacity, Q equals C delta T. Example 5.9, how much heat, so when you're asked how much heat, you're being asked for what is Q required to raise the temperature of, here's our mass, 5.0 grams of aluminum from 300 to 320 Kelvin. So this is our initial temperature and this is our final temperature. The specific heat of aluminum is CS equals 0.90 joules per gram Kelvin. So this particular example is heating one object. We're going to have a lot of different scenarios, and so I like to kind of identify the scenario that we're looking at. And when you're heating an object, we just use Q equals MC delta T, Q equals MCAT, and so we're solving for Q, where we have a mass of 5.0 grams times a specific heat of 0.90 joules per gram Kelvin times, and we'll do final temperature 320 minus initial temperature, which is 300, and this is Kelvin here. You'll notice that the Kelvins cancel and the grams cancel, and we're left with joules, which is what the unit of Q is supposed to be. So when I do this math, I get a Q equal to 90 joules. Understanding heat capacity. Notice that when the same quantity of heat is added to two different samples, the material with the larger heat capacity experiences the smaller change in temperature. That's going to be something important to understand. The larger specific heat of aluminum indicates that 1 gram of aluminum is more efficient in storing heat than 1 gram of iron. So we're looking up here at these examples. Notice iron has a smaller specific heat and aluminum has a larger specific heat. So because this has a larger specific heat, it's going to have a smaller change in temperature because of the amount of heat that it can store, as opposed to this smaller specific heat is going to have a larger change in temperature. Calculations with heat. There are really only two basic ways that heat is involved in chemical calculations. Specifying chemical. Two equations for heat. Heat is added or removed and the object changes temperature. So anytime you're seeing a change in temperature, you have to use an equation that's got a delta T in it. And typically this will be the equation that we use. The other scenarios is if heat is used for a chemical or physical process, but it's at a constant temperature. Temperature is not a factor because it's not changing. And so we would actually reduce down to this equation where Q is equal to the delta H times the moles. And this is at a constant pressure process. Extensive properties. Suppose you were paid $2 to move some bricks. Before agreeing to do the work, you would immediately ask, is that $2 per brick, $2 per hour, or $2 for the whole job? Clearly you want to know the total expected pay, so you ask $2 for what? Extensive properties like energy, heat, enthalpy, and heat capacity depend on the amount of material present. You must always pay attention to the units and determine what the question asks you to find. For example, total pay, if you did $2 per brick times 20 bricks, or total heat capacity, which is the amount of heat capacity times the amount in grams that we are dealing with, or the delta H total, which is dependent on the amount of the substance that we have. And so this is just to imply that the amount of the substance is a large factor. Example 5.10 or 5.10. Now this is specifically a scenario where you have a hot object and a cold object and they are placed together with one another. This is also known as in thermal contact with each other. So we'll label this type of problem as two objects of different temperatures in thermal contact. It's also prudent to remember that heat moves from hot to cold, or from the hot object to the cold object. So the information we're given, a 10-gram piece of solid copper, so we have a piece of copper, at 300 Kelvin is placed in thermal contact with a 9-gram piece of solid aluminum. And so we have a piece of copper in contact with a piece of aluminum at 360 Kelvin. What is the final temperature of these materials after thermal equilibrium is established? So first, what I want to impress upon you is that whatever amount of heat is lost by one of these objects is the amount of heat that's gained by the other. And remember that heat is represented with Q. So because the copper is at 300 Kelvin and the aluminum is at 360, the heat is going to move from hot to cold. So we expect the heat to be lost by the aluminum and gained by the copper. So we could say this: the amount of heat gained by the copper is equal to the amount of heat lost by the aluminum. And so we can have this equation right here. Remember that the equation for when temperature change occurs is Q equals MCAT. Q equals MC delta T. So the way this is set up, that means that the M times C times delta T of the copper is going to be equal to the negative M times C times delta T of the aluminum. And so now we've gotten to this place in our equation. I'm going to go ahead and plug in the information that we've been provided in the example above. We have a 10-gram piece of copper, so we'll have 10 grams of copper times, and they didn't give it to you in the problem, but you would be provided this information that the specific heat of copper is 0.38 joules per gram Kelvin times, and we'll have a temperature change of, we don't know the final temperature. That is what we're trying to figure out, is what is TF. So I'm going to write TF minus its initial temperature of 300 Kelvin equals negative the mass of the aluminum, which is 9.0 grams, times, again, you would be provided the specific heat of aluminum, 0.90 joules per gram Kelvin, times, we don't know the final temperature, minus the initial temperature was 360 Kelvin. All right, so Now that we have set up our equation, then we can go through solving the equation. I'm going to simplify by multiplying these two values to each other. We'll get 3.8 TF minus 300 equals, and then over here we'll have negative, multiply these two to one another, 8.1 TF minus 360. Now I'm going to distribute here and here, here and here, and after I distribute I get 3.8 TF minus 1140 equals negative 8.1 TF plus 2916. Now we're going to simplify. I'm going to move my TFs and combine them, and I'm going to move my 1140 over here to combine with the 2916. So I'm going to add 8.1 to both sides, which is going to give me 11.9 TF, and then I'm going to add 1140 to both sides, which is going to combine with the 2916 and give me 4056. And now I can just divide both sides by 11.9, and I get a final temperature equal to 341 Kelvin. And this answer should make sense because it's somewhere in between the original 300 and 360, because they should reach equilibrium somewhere in between their two temperatures. And so this represents the final temperature of both objects once they reach a state of equilibrium. Now, let's talk about a chemical or physical process that has no change in temperature. And so when you have a chemical or physical process with no change in temperature, we're going to have a different equation than we've been using. So in example 5.11, we're going to calculate the heat involved when 12 grams of ice melts at 0 degrees and 1 atmosphere. We're given a temperature, but it's not changing. It's remaining 0 degrees during the entire process of melting. And we've been given a delta H of fusion, 6.01 kilojoules per mole. So I've identified what type of problem we're looking at, the heat due to a phase change, specifically ice melting. And so this is going to be the equation Q is equal to delta H, in this case fusion, times mole. It's really just the common equation is Q equals delta H times mole. It's just that our delta H can be for melting, can be for vaporization, sublimation, or a reaction. And so we're going to specify fusion in this case, since that's what we're dealing with. And so we've been given the delta H is 6.01. It is very important to recognize that what we've been doing, Q equals MCAT, is dealing in joules, but in this equation we're going to end up with our Q in kilojoules. And it's important because later we're going to be having combinations of the equations, in which case you're going to have to modify the joules to equal kilojoules or vice versa, times the amount in moles of the ice. And if you don't recall, when you take the, here's the equation, moles is equal to grams per mole, molar mass is equal to the grams per mole. And so this is the equation you can use to quickly recognize that if I take the 12 grams of ice that I'm given, which is just H2O in the solid form, and if you divide it by the molar mass, then you would have this amount in moles. So you can always take grams, divide by the molar mass on the periodic table, and that gives us moles. Rearranging this, I get moles is equal to grams divided by the molar mass. So these are two equations that are really good to have in your back pocket. So when I do this math, I get Q is equal to 4.00 kilojoules. Notice that the this is in moles overall, and the moles and moles cancel out and leaves us with kilojoules. And this is telling us that it's going to take 4 kilojoules worth of heat in order to completely melt this 12 grams of ice in order for it to be fully a liquid. Example 5.12, calculate the heat involved when 12 grams of oxygen is converted to ozone at a constant temperature. So there's no change in temperature, which leads you to want to use the equation Q is equal to the delta H, in this case of reaction, times moles. And so I'm going to denote here that we are dealing with a chemical reaction in order to solve this problem. So if I wanted to use this equation, Q equals, then my delta H of reaction is given to me here, which is 284.6 kilojoules. But we have to take into account the stoichiometry of oxygen in the reaction. And so it's going to have to be this delta H of reaction, and we have to divide by the 3 moles of oxygen to solve this problem, times, and then we'll have moles, which is 12.0 grams of oxygen divided by its molar mass from the periodic table. And when we do all this math, we get a Q equal to 35.6 kilojoules. Now, I actually do not prefer this method. When I see a problem like this, when I see an equation and a delta H, I actually go straight to using stoichiometry and the delta H value. And so what we've learned thus far is take the 12.0 grams of oxygen, change from grams of oxygen to moles by using the molar mass in the periodic table, and then use this constant right here, that for every 3 moles of oxygen that reacts, we have a delta H of 284.6 kilojoules. And when you do this math, you're going to get the same thing. However, I feel like this method is easier to keep up with as opposed to remembering to divide the delta H of reaction by the 3 in this case right here. But the fact is, this is the kilojoules per mole. And so since you have a total of 3 moles of oxygen, then you need this to be in a per mole basis, and that's why we divide it by the 3. But if you don't want to remember and think about all that, then you can just use your dimensional analysis like we've been learning. We have 3 note cards for this section. Here's our first note card for this section. Heat capacity. The material with the larger heat capacity experiences the smaller change in temperature, and I have this summarized here. Larger C equals a smaller delta T. The equation is heat is equal to the total heat capacity times the change in temperature, where this is the final minus the initial temperature. C is the ability of a material to store energy, and it depends on the atomic structure and the amount of the material. There are 3 ways heat capacity can be specified. They can be specified per gram, per mole, or the total heat capacity. And these are the 3 equations that relate to that. There are 2 basic heat calculations. Heat is added or removed from an object causing a temperature change. Temperature change being the key, which means you use the Q equals MCAT. If you have, say, 2 objects in thermal contact, then it's going to be the MCAT of object A is equal to the MCAT of object B. Or heat is used for a chemical or physical process where there is no change in temperature. So we have change in temperature versus no change in temperature. This is the equation for no change in temperature. Q is equal to delta H times mole, and it just depends on if we're dealing with a chemical reaction or a phase change like heat of fusion, heat of vaporization, or heat of sublimation. So you might have a scenario where you say dissolve a salt into some water, in which case you do have a temperature change in the water that occurs, and so we're going to have MCAT of the water, A, or the solution, is equal to, and then the amount of energy that was released from the dissolving process is going to be something that is at constant temperature, so that would be delta H of that reaction times the moles. So it's just an example, but we will be working through some of those. We're going to watch our units. C is given in joules per gram Kelvin, but delta H is given in kilojoules per mole. And so when you have a combo equation like this, you have to keep in mind that this side is going to be calculated in joules, while this side is being calculated in kilojoules, and we're going to have to make a match. Finally, this is a heating curve, or phase changes for any substance. And we start out with solid, we're going to melt, go to liquid, we're going to boil, and then go to a gas. Notice that everywhere that the graph is moving in an upward direction, that is a change in temperature. And so the equation Q equals MCAT is going to be used at those locations. But when you have a plateau, this is where temperature is constant. And so you're going to be using the delta H times the moles, depending on if it's fusion or vaporization if it's boiling.